This PPT is visible now?
Yes, sir.
Okay. So last class we started with unit 5, that is module 5. In that we have 3 sub chapters that I told you about flow past immersed bodies. Already have shared one lecture so that you can just go through. So in that we can go into study the drag and lift forces when the body is moving. Okay, when the body is moving in a given fluid, it may be air, liquid, or gas, any type of gas like that. When a body is moving, how it is going to experience the drag or the resistance force from the fluid, or it is going to experience some lift or drag to the earth. So that we have in the flow past immersed bodies. So for this, the best examples are these examples you can just observe. So here in this example, I have taken 2 vehicles where this I'm just trying to give the example. Okay, lecture is already shared. The examples for that flow past immersed bodies is, we are going to assume the entire body is in the fluid. Okay, it is immersed inside the fluid. So on the land, if you see, we can observe such type of vehicles like truck or car. You can see where the fluid movement is going to take place about this body, and depending upon the body shape, you can observe the body shape is tilted towards the earth. So what is going to happen? As you go on increasing the speed, the air resistance or the air pressure is going to applied on the body or the surface of this entire body. So because of this inclined bodies towards the earth or the ground, the bodies will be maintained on the ground itself, so that due to friction and control of the vehicles will be very easy for us. For the same body shape, if you see for the aeroplanes or some other applications, the blades or the what you can say the wings of the aeroplane are little bit tilted. Okay, tilted above from the ground while taking the takeoff. So in such situations, as you increase the speed of a vehicle with the blades or the wings tilted above the ground, so in such conditions, the opposite phenomena will occur, where lift force will be higher than the resistance forces. So here in the land vehicles, you can see the resistance force of the or the drag force of the air is more, lift force is less. If any lift force is there, the vehicles would have flied over the land. Okay, that should not happen, because we will lose the control over the vehicles. But for the aeroplanes and other equipments or the vehicles which are flying in the air, those are also immersed in the atmospheric air. So in that conditions, we need to take the lift. So that to create more lift than the drag force, we are going to tilt the blades above the ground. So once it increases the speed, so depending upon the lift force, which is more than the weight of the vehicle itself, so that can lift the entire body. Okay, so that we are going to discuss, or we have discussed in this flow past immersed bodies, and the simple expressions are there according to the lift and drag, so that you can go through. And in that, we have solved many problems. So how the bodies are going to behave with the different drag and lift forces. Okay, and we are going to find the coefficient of drag and friction, or the coefficient of lift. Okay, then also we are going to discuss in that chapter like how the different bodies are behaving. Like say for example, a plate is kept normal to the air movement. It is also called as a bluff body, because the resistance of the air is very high compared to the lift or any other activities. The streamlined bodies are nothing but the such type of bodies, where in the plain wing blade or the plain design, if you see here, the streamlined body is there. The body lines, if you see, these are helping us to float or easily move in a fluid. Okay, so this fluid here, it is atmospheric air. For the ships and other submarine, if you consider, the body will be similar, but it is moving in a liquid. So maybe liquid may be different, the bodies are in different shapes, or the body may be kept constant in some experimental conditions or some other applications. Maybe fluid will be in stagnant condition. So it all depends on the different conditions when operating. So these type of bodies which are helping to achieve more lift force than the drag forces or the resistance forces, such type of bodies are called as streamlined bodies. Or you can also say the aerofoil shapes. So such type of bodies are going to have or experience different type of forces. So that is discussed in flow past immersed bodies. Then next we took the laminar flow and viscous effects. So in this small chapter, we discussed in the last class about deriving the Hagen-Poiseuille's equation, and we also discussed how the laminar, transitional, and turbulent flow is described using the Reynolds number. Okay, so we by using the shear force in the fluid particles when it is moving in laminar flow, that we considered as an element, and we took shear force acting on that and velocity distributions. Then we found out from that velocity distribution the maximum, average, and uh, low velocities or the minimum velocities. So using those equations, today we'll solve some numericals on the Hagen-Poiseuille's equation. Then next we'll take the laminar flow between the parallel plates similar to the our Hagen-Poiseuille's equation, which is used for the pipe. Okay, Hagen-Poiseuille's equation is for laminar flow and viscous effects which are happening in the pipe. That is for using Hagen-Poiseuille's equation. If it is between plate, we are going to use similar type of different equations for flow between two parallel plates. Means the plate will be a surface which is not a circular shape, it will be a flat surface. So between those flat surface, if the flow is taking place in the ducts or some examples, so in such conditions how these equations will change, and we are going to solve the numericals. So in the flow between parallel plates, we are going to just list the equations, and we are going to solve some numerical examples. Okay, so today we'll try to complete this part, and next class we'll try to go to the compressible flow. So this is also a small chapter. We'll look at into the compressible flow in the next class. Again, just recalling the earlier topics, that is a Reynolds number. So as the Reynolds number, if you plot versus the head loss due to friction over a given length of pipe, if you plot the graph, then we can just observe how the Reynolds number is going to vary with respect to the friction loss due to head loss due to friction and this length of the pipe. So depending upon the Darcy-Weisbach equation, you can recall here once again, because in the Darcy-Weisbach equation, it is not differentiated from the laminar, transitional, or the turbulent flow. Okay, but the Hagen-Poiseuille's equation, if you see, that is only for the laminar flow, which we can apply the Hagen-Poiseuille's equation. So here in this graph, we can just segregate depending upon the Reynolds numbers less than 2300 or 2000, it will be in the laminar flow, and between 2000 to 4000, it will be in the transitional flow. And if in the case, if the Reynolds number goes to above 4000 or 4 into 10 raised to 3, then we are going to differentiate it as a turbulent flow. Okay. So this we already discussed in the last class. Now we'll take some numerical examples. So I'll just go through this theory behind these numericals once again. So we discussed in the last class how to derive a Hagen-Poiseuille's equation or the pressure head difference in the pipe flow when it is having a laminar and viscous effects. Okay, so for that we discussed about the shear force distribution. So shear or shear stress distribution like tau equal to minus dou p by dou x r by 2. So it is in the right side direction. So minus sign is taken here. Then we discussed about velocity distributions and maximum shear stress distribution. So velocity distribution, if you just recall the equations, so we found out that velocity at a given radius can be found out by using 1 by 4 mu dou p by dou x into r square, where c is the constant of proportionality. After substituting, one can use this final formula, that is minus 1 by 4 mu dou p by dou x into r square by r square. So this r square by capital R square minus r square is at given radius. This capital R is the total radius of the circular pipe. Okay, this small r square, it is at a given distance from the center at which you want to find out the velocity. Then using these equations of velocity, we found out the maximum velocity point. So maximum velocity point in the sense, exactly if you put this small r 0 means at the center. As per the geometry, I am going to consider the center of the pipe flow where radius is considered 0. Small radius is considered 0. Full pipe radius remains as it is. In such condition, one can find out after substituting the pressure values, the distance, the viscosity of the fluid, and total radius of the pipe. So once you substitute all these values, that is 1 minus 1 by 4 mu dou p by dou x into capital R square. Okay. So by using this equation, one can find out what is the maximum velocity taking place at the center of the pipe. So that profile is shown here. At the center, how the maximum velocity is taking place in the laminar condition only. For that, you can use this equation, Umax. Then we gone through the finding the discharge of the pipe where we need average velocity. Okay. So using that average velocity and the flow area. So using that, we found out the average velocity, this discharge by average velocity. That is U bar is minus 1 by 8 mu dou p by dou x into capital R square. So either you can use the average velocity or just by using this radius values, one can find out the discharge through the given pipe. Then we observed that the maximum velocity at the center of the pipe which is flowing, if you take the ratio to the average velocity, then the ratio of these two, maximum velocity to the minimum velocity or the average velocity, is 2. So in the test or the examination, the question may be on derive the equation for ratio of maximum velocity to the average velocity as 2. Okay, maybe for 10 marks. So here also you have to start with shear force distribution and velocity distribution. So using those equations, you can derive the ratio of maximum velocity at the center of the pipe to the average velocity in the pipe as 2. Okay, then one more question may be on the Hagen-Poiseuille's equation you need to derive. So for this equation, the marks may be up to 12 marks, may be asked in the exam. If it is IA test, it may be 6.5 or something. So you can shorten some steps. But again, for this, you have to again derive for the dou p by dou x. So whatever the dou p by dou x we discussed here, change in the pressure or the difference in the pressure for a given length of pipe, same thing is expressed in P1 minus P2 by delta x. So that delta x is taken as L here. Okay, so by just replacing those dou p by dou x in the average velocity equation, that we have converted into pressure head difference. And then finally, we are going to write this equation, that is P1 by P2 by rho g as 32 mu into average velocity into length divided by rho g d square. So here we have divided both the equations by, or both the sides by rho g. Okay, so this equation is very important for us to solve the numerical examples, which is called as Hagen-Poiseuille's equation. So this equation will help us to find out what is the pressure difference between the pipe flow for a given two different points, or I can tell the head loss due to pressure difference. Okay, so that head loss due to pressure difference is shown here, HF, in the laminar conditions. So in such conditions, we can use these equations and you can solve the problems. And if again, in other conditions, laminar and turbulent flow, if you want to find out the head loss due to friction, then you can use this 4FL U bar square divided by 2 GD. Then what they have done is to find out the friction factor by this Darcy-Weisbach equation. Either you can use the Darcy-Weisbach equation directly, or if you don't know this HF or diameter of the pipe or any other values, then you can equate these two equations to find the friction factor. So by equating these two, Hagen-Poiseuille's equation and Darcy-Weisbach equation, then he found out that friction factor is around 16 divided by Reynolds number, or 16 divided by rho into average velocity into diameter divided by mu. So either you can remember this 16 by rho Vd by mu, or you can remember 16 by Reynolds number. So by this, one can find out the friction factor also in the laminar flow, because in the laminar flow, apart from the viscous forces, the friction force between the pipe as well as the liquid is also more. Because of that, the velocity between the pipe wall and the first layer which is in contact with the pipe, the first layer which is in the contact with the pipe, that layer of oil will be having more friction factor. Okay, so this all things we discussed in the last class. Now we'll take some numerical examples using these equations. Okay, Hagen-Poiseuille's equation, maximum velocity to average velocity, then shear force or shear stress distribution in the pipe flow. So for that I have took some problems here. So you can note down these problems. These are the numerical examples on laminar flow in the pipe or using the Hagen-Poiseuille's equation. So first problem is calculate the pressure gradient along the flow. So whenever this term comes, pressure gradient along the flow, means it will be a Hagen-Poiseuille's equation or the equation which indicates P1 minus P2, pressure gradient. So that equation you have to recall. Then we need to find out the average velocity, that is U bar. Average velocity means we know the relation that U max by average velocity is 2. Using that relation, one can solve this problem. Just a minute. It is for two stationary parallel plates he has given. So I think it is a different problem. Correct. Is it a pipe? Yes, now it is circular pipe. Yes, here you can see a crude oil of viscosity 0.9 poise and relative density 0.9. Please focus on the given data here. I'm sorry that I have taken the problems earlier were on parallel plates. This we'll discuss later. Before that, we'll discuss the circular pipes. On the circular pipe, how it is varying. So note down clearly the given data. Viscosity is given directly, that is dynamic viscosity mu equal to 0.9 poise. So once this unit is given, convert that into Newton second per meter square. So for that, we need to divide by 10. 0.9 by 10 if you do, you will get around 0.09 Newton second per meter square. This is in SI unit. Viscosity is given and relative density. Relative density is density of the given fluid like oil to the density of the standard liquid, that is water. So that if you consider, I can find out the other requirements. So relative density is given. So this oil is flowing through a circular horizontal pipe. Okay, so this is flowing through a horizontal circular pipe of diameter 120 mm. So if you want to solve the problem by diameter, you can consider diameter. If you solve the problem by radius, using radius, you can convert this into half. So 120 mm radius or the diameter is given, that you can consider. Length of the pipe at 2 points to find out the pressure difference is 12 meters. So for a given length of pipe, 12 meters only, we are finding the results. So that length of pipe is given. Calculate the difference of pressure at the two ends of the pipe. So I want to find out difference of the pressure P1 minus P2 at two ends of the pipe if 785 Newton of oil is collected in 785 Newtons. Okay, weight they're telling, they're not telling the rate of flow. If the 785 Newtons or the weight of the oil is collected in a tank in 25 seconds. Okay, so in 25 seconds, they are collecting 785 Newton of oil. So now we'll analyze this problem. So first we'll recollect once again the given data here. Viscosity of the crude oil is given, mu equal to 0.9 poise. So in SI unit, it is 0.09 Newton second per meter square. Then relative density is given 0.9. So from this one can find out the weight density. Okay, this will be useful for our solving the problems. That is weight density is 0.9 into 1000 into 9.81. So that will be 8,829 Newton per meter cube. Then they have given the diameter of the pipe, that is 0.12 meters. Then length of the pipe is already given in the assignment, that is, or the pressure difference points, the length is 12 meters is given. Then weight of oil collected in 25 seconds is 785 newtons. So these all data is given in the problem. Now we can recall the equation for finding difference of pressure at these two ends. So once you find out this thing, our problem is over. So I'll recall the Hagen-Poiseuille's equation for the pressure difference between the two ends. That is P1 minus P2 by L equal to 32 mu into U bar divided by D square. So please recall the theory part and this equation. So Hagen-Poiseuille's equation in diameter, if you see, it is P1 by P2, P1 minus P2 equal to 32 mu U bar L divided by D square. Okay. The same equation is recalled here to solve the problem. Now using this equation, what all things we need here? P1 minus P2 we need to find out. Mu is given in the problem. U bar is the average velocity. It is not given in the problem. Length between the 2 points is given 12 meters. Diameter is also given. Now for the average velocity, as we discussed in the last class, average velocity is for entire cross section of the pipe, whatever the flow is coming out, for finding the normal discharge or any type of flow, whenever you are finding the velocity, that velocity is considered as average velocity of the flow. And here we are not focusing on maximum velocity or the zero velocity at the wall, because we are not finding the maximum discharge here. We are just finding the discharge. What is the average discharge for a given pipe flow? So to use that, here we are going to find out this discharge using the weight density formula. So for that, you can just note down here 785 newtons per second. Okay, so Newton per second is the weight, what is that? Weight collected per second. So weight of oil collected per second, if you see, that you can multiply with the given discharge. Or discharge can be given as weight collected per second, that is Newton per second. Then using this formula, all of you know, discharge is always mentioned in meter cube per second in SI units. Now using this per second values, any per second values, can we convert that into meter cube per second? That we can think of. So for that, we have 785 Newton per second value. Okay, that is the weight of oil collected per second. Earlier in some problems we discussed liter per second oil is collected, meter cube per second oil is collected, something like that, or water is collected. But here in this problem, weight is given. Now you can just focus, anything is related to weight in the problem. That is, we found out weight density as Newton per meter cube. Now 1 Newton here and 1 Newton in this 785. If I multiply or divide something, if I do with these two values, I can cancel this Newton. Is that clear? So keeping this in mind, what they have done is discharge value. They are not using this average velocity or this area of the cross section of pipe. Directly what they have done, they have used these two numbers, weight density as well as weight per second, whatever is oil is collected. Using those two values, they have taken ratio of weight of oil collected per second divided by this weight density value, what you found out, 8,829 Newton per meter cube. They have cancelled this Newton and they found out the value in meter cube per second. Okay, this is the new type of step to find the discharge. Okay, if directly we don't know the average velocity, then we can go by this formula or this procedure. If the weight of the liquid or weight density is given, this discharge step is clear to all? Yes. All of you understood the discharge, how they found out in meter cube per second?
Yes, sir.
So alternately in the problem they had given Newton per second value and the weight density indirectly given in the relative density value. So in any such type of examples, you have to try to interrelate between the same units and you have to try to get the new units. So like that is given. Now from this discharge, once the discharge value is known, now one can find out the average velocity because we know the discharge formula, that is area into velocity by continuity equation. So using that continuity equation concept, now discharge is known from the given data itself. Okay, or average velocity, if you recall the derivation, one may ask, sir, what about the derivation? Until now you told about derivation where we found out the average velocity or maximum velocity equations. Why not we are using these things? Can anyone tell me why we are not using this equation? U bar equal to minus 1 by 8 mu. Mu is given dou p by dou x into r square. If I use this equation, easily I can find out U bar and I can find out discharge also. The problem here is the pressure difference is not known still. We don't know the pressure difference. We know length 12 meters, viscosity 0.9 is given, 0.9 poise is given, r square, the diameter of the pipe is also given. But this, whatever the question is asked, dp, until now, we have not found out the pressure difference between these 2 points. So that's why I am not using the equation which is used from the derivation. Alternate to this, I am using some other method just to find out this unit. That's why these units and dimensions are very important. If you know the unit of discharge meter cube per second, then I'll think somewhere here after conversions, I may think here Newton per meter cube is known, Newton per second is known. So somewhere I can divide or multiply whatever I can do, I can find out meter cube per second. So same thing they have done here. Using just dimensions and relations, they have found out the answer. Now from that continuity equation, other than derivation equation or the Hagen-Poiseuille's relations, now I can use velocity is equal to Q by area to find the velocity from continuity equation. So here, this velocity we can tell as a average velocity. Okay, so all the data is known to us now. So discharge is 0.00355 meter cube per second divided by area of the cross section of the pipe, that is pi by 4 d square. Okay, now if I find out the average velocity, so average velocity, if I tell it is not at the center or the velocity is not at the inner surface of the pipe, it is in between. So that average velocity is, or it is average of all the particles throughout the cross section of area of the pipe. That average value is 0.314 meter per second. Okay. So whenever you see the pipe flow, you have to just assume the pipe flow is taking place with the average values. If you see the center, the flow is at very high velocity. At the wall, the flow is very with less velocity. So keeping that in mind, we are going to take the average. So at a given instance, what may be the average velocity of all the particles of water which are coming out, or oil which is coming out of the pipe. So that average velocity is 0.314 meter per second. So in between maximum and minimum velocity, there lies one point at which the velocity of those particles of the liquid for a given ring of that oil flow will be around 0.314 meter per second. Okay. So next we need to find out the pressure difference. Now see here in this formula we got a mu value, then we got average velocity value we got, then we got length of the pipe already given, diameter is also known. So from this one can use the pressure difference equation and can find out what is the pressure difference value. So before that, what they have done, whether the flow is laminar or not, they have checked. So if it is asked, you can find out whether it is laminar or turbulent. Otherwise, you can also directly use this pressure difference equation because we cannot consider always, because in the problem itself, they are asking the pressure difference we need to find out. So pressure difference means we have to go by Hagen-Poiseuille's equation only. So you can use this equation. You can find out the pressure difference. That is 32 into 0.09 is found out here. Then U bar average velocity is 0.314 into length between the 2 points to 12 meters. Then the diameter, that is 120 mm is the diameter. So in meters it is 0.12 meters. So 0.12 square. So once you substitute all these values, I can find out pressure difference. So pressure difference between 2 points, and just recall this sketch. Pressure difference between 0.1 and 0.2 between this length L is how much we are getting? 753.6. And about units, even if you don't know or don't remember these units, please follow these units given in the problem. And in SI units, once you convert, one can find out this unit as Newton per meter square. Okay, so we got pressure difference between those 2 points, 753.6 Newton per meter square. Now, if in the question, if they ask, check whether the flow is laminar or turbulent, okay, then I can use this Reynolds number. Then I'll find out the Reynolds number rho Vd by mu. Already I've done in the lab. I'll not focus much here. So using this formula, if you find out the Reynolds number, it is around 376.8. So as the number is below 2300, then we can definitely can tell that whatever the problem you have solved by using Hagen-Poiseuille's equation, that holds good because it is a laminar or viscous flow. Okay, that is just a final check whether it is a laminar flow or the equations applied in this problem are correct or no. Okay, now this is the problem regarding directly using the Hagen-Poiseuille's equation. Next one we can see a liquid with specific gravity. So please recall the fluid property chapter and how we need to convert all these units once again. So here specific gravity is given, that is 2.8, and a viscosity 0.8 poise flows through a smooth pipe of unknown diameter. Diameter is not given, means for the Hagen-Poiseuille's equation or any other findings, we need to find out this diameter, because without diameter we don't have any other formula. So diameter is required later, resulting in a pressure drop of 800 Newton per meter square. So pressure drop is given indirectly, delta P is given, or dou P is given. Dou P is given as 800 Newton per meter square. So here pressure difference is given, remaining values are given. I think they may be asking the diameter also. Then after the pressure drop, it is between 2 kilometer length of the pipe. Okay, the pipe is 2 kilometers. So convert this into meters, 2000 meters. The pipe length is given. Between that, the pressure drop is 800 Newton per meter square. And they're asking what is the pipe diameter. See, again, we need to find out the diameter of the pipe itself. What is the pipe diameter? If the mass flow rate is 2500 kg per hour. Now again, you can see the mass flow rate is directly given, so no need to think much. So directly convert this 2500 kg per hour into meter cube per second. Okay. So again, one by one, if you want, you can note down the given data, and later you can go on solving the problem. Now, first thing is, again, rewrite the Hagen-Poiseuille's equation. Why? Because they have given the delta P and they are asking diameter. So any equation in this laminar flow or in this chapter module 5, if any equation is relating the delta P and our diameter of the pipe, that is nothing but a Hagen-Poiseuille's equation. That is P1 minus P2 divided by L equal to 32 mu into U bar L U bar divided by D square. Okay. Now in this equation, P1 minus P2 is given how much? 800 Newton per meter square. No need to convert. It is already in SI unit. So I'll keep 800 as it is. 32 into mu. Mu is the viscosity. So viscosity was given in 0.8 poise. In Newton second per meter square, it is 0.08. So just divide by 10 and you'll get the answer in SI units. Into, I need average velocity. Now for average velocity, what you can do? For average velocity, I need the discharge through the pipe for a given area or Q by A. So discharge from the pipe is given how much? 2500. So after converting, they have found out here 0.6944 kg per second. Okay, after converting per second, they have found out it is in 0.6944 kg per second. That mass flow rate to finding the average velocity. See here, mass flow rate is nothing but a discharge only. Okay, rho AV, or it is velocity into area. So for that, what they have done, they can consider this average velocity equal to discharge by area. I hope the point is clear. In place of discharge, they are just substituting this m value, mass flow rate. So mass flow rate divided by rho, if you take, it is nothing but kg per second. Or if you want directly discharge, this you need to convert. Kg per second you need to convert in meter cube per second. Directly you can take the equation of continuity equation. That also you can do. Or else using only the mass flow rate, okay, and converting that mass flow rate into discharge. For that, what they have done, they have taken U bar equal to, in place of discharge Q, they have written m by rho. Mass flow rate divided by density of the given liquid. That is m by rho they have taken divided by area. So area of the pipe, how much? Area of the pipe is pi by 4 d square. Diameter is not given in the problem. So this is kept as it is. So you can just substitute these values. Mass flow rate is 0.6944. Then density of the given liquid. So density from the specific gravity one can find out 2.8 into 1000 into area of the pipe, pi by 4 d square. Is that clear? Now this is the relation, because here diameter directly we cannot find out, because even we don't know average velocity, how much it is. Average velocity is dependent on diameter. Diameter is dependent on average velocity. Both are unknowns. So what we have done here is, average velocity can be written as, in place of U bar, I can substitute 3.158 into 10 raised to minus 4 divided by d square. So this equation, why we have converted is to keep the formula of Hagen-Poiseuille's equation in terms of d only. Okay. Next is viscosity. It is given. Now we found out the value of average velocity in terms of diameter, because even Hagen-Poiseuille's equation is also related with or dependent on the diameter only, which is unknown. Then length of the pipe is given. 2 kilometers they have given. So we have taken 2000 meters. So in the denominator we have d square into d square. Pressure difference is also given. Now taking this d raised to 4 on the left hand side, you can find out the d value. So please, one of you use the calculator and tell me whether the diameter is, you are getting the correct answer or not. Here they are telling the diameter after substituting 32 into 0.08. So 32 is the, in the formula of Hagen-Poiseuille's equation, 32 into mu into u bar. U bar is 3.158 into 10 raised to minus 4 divided by d square. It is taken left side, into length of the pipe 2000 meters divided by this dp or p1 minus p2 is taken in the denominator. So once these all values are substituted with raised to 1 by 4, the value is, that is 0.212 meters diameter. So please check the value in calculator and tell me. Anyone found out the values? Yes, 0.212. Okay. Okay, if it is correct, then later we can just check. This check is not at all compulsory. If they ask, you can do the check for the Reynolds number or the laminar flow. That is rho Vd by mu. So rho is the density is given 2.8 into 1000. You can multiply for converting that specific gravity into density. Then average velocity found out in terms of diameter, that is 3.158 into 10 raised to minus 4 divided by d square is the average velocity into diameter d divided by 0.08. So now this diameter can cancel here, and in the denominator I have to substitute one diameter value 0.212. So once you substitute these all values, I can check one number, dimensionless number. That number is coming around 52. So 52 is less than 2000. So it is a laminar flow. Why we are checking this laminar flow? Because whether using this Hagen-Poiseuille's equation, what problem you have solved, it is applicable for the laminar flow only. If it is a turbulent flow, then other method you have to go for. Is that clear? This is on horizontal surface pipe. One more I had taken. Just a minute. Okay, I think we'll stop the discussion on circular pipes at this point. These type of problems are enough. Okay, or if you want one more, you can just go through this problem. Roughly, it is solved here. You can take this problem for a, I think, circular pipe or what. You can just see here. Yes, pipe is given. From this, again, we are going to find out P1 minus P2 value or some other unknown values. And in this problem, the extra thing is they are finding the power required or the power lost. Okay, either extra power required to reduce this loss or the power whatever is lost in the given flow, they are finding out. So this is the extra question here in this problem. Okay, later on I will share these all PPT notes. Okay, so this problem you can take it for homework. Okay, we'll stop this class now. Later, I think now 10:46. We'll meet at 11 a.m. Okay. Or shall we continue the class? Okay, we'll have the break and we'll continue later. Shall we continue the class? Shall we continue? Is there any network issues there? Okay. Now coming back to the discussions on laminar flow in circular pipe and numericals. Now we'll discuss in this class about laminar flow with viscous effects between the two parallel plates. So this already some part we have done in the Newton's law of viscosity. Okay, so in the Newton's law of viscosity we have discussed that is tau equal to mu into du by dy. In using that equation also we have solved some problems between two parallel plates to find the viscosity or velocity or the distance between the plates. Okay, similarly here, so using the similar equations to Hagen-Poiseuille's equation, we are going to derive some equations, and in the syllabus we don't have derivation or the this one procedure to find the equations. We have only the numericals. Only numericals we need to discuss in this part. Okay, so I will just explain briefly the equations and the derivation, and you have to note down these list of equations to find the shear stress, pressure difference, or various velocities in the flow between two parallel plates in the laminar conditions. Is that clear? So now you can again consider two parallel plates here as shown in the figure. So two parallel plates which are fixed. Okay. So earlier in the Newton's law of viscosity we have discussed, apart from these two plates, either one is moving. Okay. Depending upon one plate moving, how the viscosity of the oil or the velocity of the oil is going to change. That we discussed with the Newton's law of viscosity only by using velocity, then the distance between the plates and other factors. But in this, preferably, we are going to take two plates between which the oil or the liquid is going to flow, and these both the plates are fixed. Okay, any plate is not moving. Both plates are completely rigid. The only flow is going to take place. The oil is continuously flowing between the two plates. Either these two plates or the pipe, whatever you have considered earlier, this pipe or the fixed plates are not at all moving relative to each other. That thing should be the first consideration for these derivations. The next is between the point 1 and point 2. If you see the flow, okay, in between these 2 points, we are not going to consider any body like in flow past immersed bodies or measuring the any properties between the point 1 and point 2. We are not going to consider any body. What we are going to consider is the same fluid element. Okay, whatever this element is shown, ABCD element is shown, it is of the same fluid only. It is not like shown in these images. Say for example, if you take these images, here a different body is considered between the 2 points or between the flow. Okay, the body is different, the fluid is different. This comes in flow past immersed bodies. But this example, what is shown here, this example, here in between the flow, we are going to consider the same fluid elements. There is no any other particle or any other body which is kept in between these 2 points, like in pipe flow or the parallel plate flow. The next is, so if once you assume this elementary volume, ABCD volume, considered in the given parallel plates or the circular pipe, the cross-section area what is considered here is ABCD. So once it starts flowing from left to right, okay, or right to left, okay, what will happen? There will be shear forces acting. because the fluid is going to shear between the different layers, because layer which is near to the wall is flowing at a very low velocity. The layer which is at the exactly at the center, which will be flowing at a very high velocity. So between this, if you consider any fluid element, it is going to experience some shear forces. So that shear forces are shown by these equations, or the shear stress equations are shown by these equations. That is tau plus dou t by dou y into dou y. So in this problem, they have not considered R, because here we have not considered the circular area. If it is a circular area, they would have considered diameter or the radius, dou R by dou R, like that. But here what they have done, they have taken the distance between the plate as y or t. It may be dt also. But many times in our discussions, dt, if you consider it is change in time. Okay, better you can replace this t word as y. Okay, the distance between two plates, either t or y, as per your convenience. So that y is the distance between the plates. So that small change in distance is dy, they have considered. Then the pressure difference, the pressure at one face is again applying the same principle of that circular pipe or Euler's equation also. The pressure acting on the left hand side is P into dy. Dy is the height, one is width. Maybe they have taken unit width. So that's why they are considering the area of that surface AB as dy into 1. Okay, and P is the pressure force acting on the left hand side. And on the right hand side, if you see, whatever the additional pressure is there because of the flow moving side, so that is P plus dou P by dou X into dx into dy into 1. So dy into 1 is area of the surface DC. On the other side, how this pressure is increasing? This pressure is increasing depending upon this length of the flow. So that length of the flow, they have taken dx. So on both the derivations, dx is same. Okay, length of the flow, this arrow mark dx is shown here. This dx remains same in the both the derivations. Okay, now considering these all equations separately, the pressure force on the AB, the pressure force on the CD on the other side, then shear forces or the shear stress tau. Tau, if you want to find out, you can find tau, or force if you want to find out, you can multiply tau into area. So like that, they are going to find these all forces acting on the elementary fluid. So this elementary fluid, you can keep in mind, it is also like a rectangular in shape. That's why they have taken height into width. So width may be 1, height may be dy. But in the circular pipe, they have taken dr, radius into periphery of that circle. So using the same principle to balance the horizontal forces or the shear forces, here they have found out the velocity distribution. In that, they have found out velocity at any given point with the constant c1 and c2 here in this problem. So they found out velocity equation as minus 1 by 2 mu. So all of you can note down these equations. Later we are going to use the same equations in the problems. Okay, so velocity at any given point is 1 by 2 mu dou p by dou x into bracket ty minus y square. So t is the total distance between the plates, y is the relative distance, okay, from the base to the center of that point or center of that elementary fluid which is considered, that is small y. And this y, so y you can again observe here if you are getting confusion. This is dy up to this tip or up to this point, whatever they have considered, up to this surface of the element, that they have considered small y. And t is total distance between the two plates. So either you can write this as capital Y, this as small y. After deriving, they found out the velocity equation as 1 by 2 mu dou p by dou x into ty minus y square. Next, they have found out the shear stress distribution tau. So tau they have found out that is minus 1 by 2 dou P by dou X into T minus 2y. And maximum shear stress, so maximum shear stress, all of you know, it is at the wall side, wall of the plates. So plate wall both are fixed. That's why on both sides the intensity of the shear stress is same, and at the center the shear stress is negligible. So that shear stress maximum they have found out as 1 by 2 dou P by dou X into T. Okay, at y equal to T. Y equal to T means maximum point. And at the center, if you want to find out, you can use this equation, minus 1 by 2 dou P by dou X into T. Or ultimately what I can tell, it may be plus or minus, as the both equations are same. I can write it as 1 by 2 dou P by dou X into T. And this T is the total distance between the parallel plates. Okay, or if it is in the pipe, it will be like a diameter or total R, capital R, what you have considered from the center, that also you can observe. Then maximum velocity at the center. So they have taken T by 2 here at the center, Y is at the center, T by 2 they have taken. Then you can tell U is U max, or the maximum velocity at the center point. So after substituting, they found out U max as minus 1 by 8 mu dou P by dou X into T square. So just see the circular pipe equations. We'll see the circular pipe equations, U max, what we got in the U max relation. Because we need to remember these equations carefully. So here it is 1 by 4 mu, there it is 1 by 8 mu. Dou P by dou X capital R square. For the pipe flow, in the parallel plate flow, it is minus 1 by 8 mu into dou P by dou X into this T square. Next is using this maximum velocity or the average velocity, we can find out the ratio of U max and average velocity, that also can be done. And discharge equation they found out minus 1 by 12 mu dou P by dou X into T cube. Please note down all these equations which are useful for our problems. So I'm not skipping derivations, but in the syllabus only, they are mentioning that only numericals are enough in the syllabus. Numericals only. Laminar flow between parallel plates or stationary plates, numericals only. So we'll list the equations first. And derivation, if you even focus it, it is on the similar lines with the pipe flow itself. Using the same principle, they are derived these equations. Okay, now we'll see the ratio, or can see the average velocity, that is minus 1 by 12 mu dou P by dou X T square. Now ratio of maximum velocity to the average velocity in this flow between the parallel plates, that is not equal to 2 here. It is around 3 by 2. Okay. So U max to the U bar, average velocity ratio, if you see in this flow between parallel plates, it is 3 by 2. Means here in this condition, maximum velocity and average velocity is not exactly at half or this point. It is at 3 by 2. So at 3 by 2 means you can just observe from center to the wall of the plate, in between at what point you can find out the average velocity. So that point is 3 by 2. That is the average velocity point. Then next is the Hagen-Poiseuille's equation for parallel plates. Here they have shown pipe, circular pipe. It is not circular pipe. Okay, this sketch you can remove later, or I'll arrange this slide with removing this pipe flow. Okay, it is not pipe. it should be flow between parallel plates. That sketch should be shown here. Then we can get P1 minus P2 by, or P1 minus P2 equal to, for this flow between parallel plates, it is 12 mu u bar into L divided by T square. Okay. Yeah, this completes our chapter on laminar with the viscous effects. Now we'll see the numericals on this using equations of flow between the parallel plates. So note down once again the pressure difference between the flow between two parallel plates, that is, or between 2 points in flow between the two parallel plates, that is P1 minus P2, is given by 12 mu into u bar L divided by T square. Okay, that equation you can note down. Now we'll see some numericals using same equations. Yes, here I have taken the numericals. So these numericals are based on the parallel plates, two stationary parallel plates. Between that, the flow is going to take place. So today we'll solve some problems on this, and we'll wind up this laminar and viscous effect chapter. Okay. So first problem, I'll read the problem here. So calculate, the first point is we need to calculate the pressure gradient along the flow. That is P1 minus P2 we need to find out. Next we have to find out average velocity, U bar we need to find out. Then the discharge for an oil of viscosity 0.02 Newton second per meter square. So luckily in this problem they have not mentioned poise again. They have directly given in the SI units, that is newtons per second per meter square. That value is 0.02. It's directly given. Flowing between, this is very important, where it is flowing, whether it is flowing in a pipe or an open channel or in a closed channel like a stationary plate, whatever. So that depends on what type of flow is taking place in the channel. So that channel is having two stationary plates. Between that, we are going to consider the laminar effects. Okay. So it is flowing between two stationary plates, parallel plates, 1 meter wide. 1 meter wide means the width of the given channel is 1 meter wide, maintained at 10 mm apart. So distance between these two parallel plates is 10 mm. Okay, the height, the y value or the t value, whatever I had told in derivation, that distance between the vertical distance between the parallel plates is 10 mm apart, and 1 meter is the total width of this channel, that is 1 meters. And what is at the sides, we don't know. It may be a metallic channel, or it may be any construction material, okay, or it may be having some viscous effects, or it may not be having viscous effects. Here we are focusing the laminar and viscous effects only between these two stationary plates, one at the top, one at the bottom. Okay. Then the velocity midway between the plates is 2 meter per second. Now just read once again this sentence. Velocity midway. Midway is at the center. So central velocity, or also by derivation I can tell it as maximum velocity between the plates is 2 meters per second. So if the maximum velocity is 2 meters per second and the distance between the two plates is 10 mm apart, means at 5 mm distance from the base or from the top at the center, that is 5 mm apart. 5 mm distance, the velocity is 2 meters per second. Okay. So now we'll list once again the given data, whether they are in SI units or not. So viscosity is a SI unit 0.02. Then width is given in meters, 1 meter. Distance between the plate is given in mm, so they have converted in meters. Next, velocity is given, that is central velocity is maximum velocity, Umax. So Umax is 2 meter per second. Now taking all these details, in the problem they are asking totally 3 components. First is pressure gradient we need to find out. Then we have to find out the average velocity. So average velocity is not given here. Only Umax is given. You need to find out average velocity. Also, we have to find out discharge of oil. So first coming to the pressure gradient, that is dP by dx or P1 minus P2. So once you recall that equation, dP by dx, okay. So from the derivation we have dP by dx. I close that 1 minute. Yes. So here P1 minus P2 is 12 into mu. Mu is given. Here in this equation, I need average velocity, not the maximum velocity. So average velocity U bar is required. Length is also given. And T square. T square is the distance between the plates. That is also given. So what we have to do now is, before going for this dP by dx formula or P1 minus P2 formula, what I will do is, I will find out the average velocity. Okay, so for finding that average velocity, either what you can do is, you can go by Umax by U bar is 3 by 2. From this one can find out what is the average velocity. So from that I can tell the average velocity U bar is 1.33 meter per second. By this step, I have solved the part of the problem. Average velocity is 1.33 meter per second. Directly this value I can substitute in the P1 minus P2 formula and I can tell the value. So P1 minus P2 may be minus 3200 Newton per meter square per meter, or else, or another thing what you can do is, from the derivation you can recall the maximum velocity formula. So that maximum velocity formula is Umax. Umax is minus 1 by 8 mu dou P by dou x into T square. Here dou P by dou x is the pressure gradient, difference in pressure for a given length, that you can find out. As Umax is given in the problem, mu is given in the problem, T is also given in the problem. So once you find out dou P by dou x, you can multiply this distance between the points dx with the answer. So by that also you can find out dou P. But by both the methods, the value should be same. Any one method you can follow. So either you go by dou P by dou x. So this, as I told, it denotes minus 3200 Newton per meter square per meter. This per meter is because of this dx. This dx you have to multiply here. So what is the distance between 2 points? Have they given? Wide and height they have given. Distance between 2 points they have not mentioned in the problem. Okay, so maybe because of that they are writing only this value dP by dx as Newton per meter square per minute. Sorry, per meter. By this problem or by this step, if you go, the complete. Yes.
The distance between two parallel plates is given.
Discharge is given. Okay.
No, sir, distance between two parallel plates.
Discharge between two parallel plates we need to find out. Discharge between. Discharge between two.
Sir, she said distance between two parallel plates is given.
Distance between two parallel plates is vertical distance, not the length. Just a minute. We call the earlier problems. Length between the flow, if you see, earlier they had given this length. I think here, 2 kilometer. If you see this problem, earlier problem, 2 kilometer length of the pipe. Like this, in this problem, they have not mentioned what is the length of flow or what is the length of the plates. Is that clear?
Yes, sir.
Yeah. Please be careful. Distance between the stationary plate is given correct, but this is distance between is bottom to height. What is the distance between two parallel plates? That vertical distance is given, not the horizontal distance. That is one thing. One more horizontal dimension is given, but that is how much is the channel width is there. So totally, if you consider a rectangular duct, it is having 1 meter by 10 mm. That's all. Okay, cross section they have given, not the length. So that's why they have not substituted this dx value. The dx value is not given. So they are writing in Newton per meter square per meter only. So either by this you can find out, or you can go by this equation also. Both are same. P1 minus P2. Yes, in this if you see here, this L value not mentioned in the problem. So they have kept it as P1 minus P2 by L is equal to 12 into mu into U bar divided by T square. If you take this equation, the value should be 3200, that is minus 3200 Newton per meter square per meter. So if any time the length is not given, you can assume it as 1 meters. Because we are finding per meter means, what you can do now here is just multiply with 1 and tell that dP is minus 3200 Newton per meter square. This is for per meter length. What is the loss? Because they have not mentioned 1 kilometer, 2 kilometer, nothing. I can tell, removing this per meter, what I can do, I'll multiply minus 3200 Newton per meter square into 1 meter. 1 meter length I'll multiply. Then I can tell the pressure drop or the difference in pressure is minus 3200 Newton per meter. Okay. So once this dP value is known, or the Umax value, average velocity, which is asked in the problem, that you can find out between the parallel plates by using this relation 3 by 2. If it is a circular pipe, I have to write Umax by U bar is 2. So by this relation, I can find out average velocity between these two parallel plates is 1.33 meter per second. This is the average velocity. Then we'll find the discharge. Discharge is average velocity into cross-section area of the flow. So luckily in the problem, cross-section area is given 1 meter by 10 mm apart. See the channel, you can just imagine the height is 1 meters. Okay, height is very high. Width is only 10 meters apart. It is just like a vertical pipe or vertical some small piece of strip like that. Sir, yes.
Sir, but length is not given, no? That 1 meter is wide. It is breadth, right?
Yes, 1 minute. Yeah, here earlier I told a length was given 2 kilometer. We were multiplying here 2000. Okay. Here we were multiplying 2000 length. For 2000 length, we were finding some unknown values. Similarly, what I am doing here is assuming 1 meter, I can tell. Here they have not assumed in the problem. But even if we assume, I can tell this value in minus 3200 Newton per meter square per minute per meter. Only that we can do. Apart from this, what you can do is you can imagine one of the length, like 2 meters or 2 kilometers you can imagine. Then after multiplying that, you can tell the pressure drop for a given length, 2 kilometer or 1 kilometer assumed value. Even you can assume. That is not a problem. But here, as the value is not at all mentioned in the problem, what they are doing, they are writing the both units for a given distance. So anything if you divide by value, that I can tell it as for 1 meter, for 1 second, for 1 hour like that. So for given 1 meter, it will be minus 3200 Newton per meter square. Okay. You can mention here, you can write a note that length of the flow is not mentioned in the problem. So assumed length per meter, the value will be this much. Or assumed length for 2 kilometers or 1 kilometer, how much value you get, you write for given distance. This will be the pressure difference. Is that okay?
Yes, sir.
Okay. So now discharge, we know the velocity at the average point, velocity, average velocity we know. Then area of the flow is the cross section area. So 1 meter is the height, width is 10 mm. You can just multiply and you can find out the discharge or the average discharge from that channel. That channel is 1 meter height, only 10 mm width. It is like a just one wall you can see, one section of wall, 1 meter height, 10 mm width. Like that it is flowing. A thin section of oil is flowing. That flow is 0.0133 meter cube per second. The only problem here is in this problem is finding this dp. We are not finding dp, but we are finding dp related to some distance. Okay, so take another half minute, go through this problem once again. We'll take the next problem. Okay, the next problem is
Excuse me, sir.
yes.
Sir, in previous problem, the discharge is area into velocity, right?
Yes, area into velocity.
So, but for area, we don't know the length, right? Like
Yes,
T is distance between two parallel plates.
yeah, length we don't know, correct. So whenever, if you recall the earlier discussions, okay, in the flow measurement, the flow through, say for example, orifice or the flow in lab only. In lab, you have conducted many experiments. You have found out the discharge, correct? So there, if you recall, we are using the cross-section area of the pipe. Cross-section area of the pipe, we need either the diameter of the pipe, or if the channel is there, we need the cross-section area of the channel. That is height into width, not the length.
Okay, okay, sir, got it.
Okay. Or in the lab, if you just observe the outlet of the pipe where the water is flowing from the pipe to the tank, that one meter cube tank, whatever the water is flowing, in that we are using the area of cross section of that channel. It may be pipe or anything. The channel cross section area we are using, where length is not required for finding the discharge. So that's
Yes,
why,
sir.
yeah, if you talk about that area, it is height into width. So height into width is given in the problem. So that you can directly find out. Only problem is finding the pressure difference. Directly we cannot find out pressure difference as we don't know the length. Or you can assume length and you can multiply here and you can mention in the problem. For assumed length of the pipe or the length of channel flow, this is the pressure drop. Or keeping as it is per meter, how much is the pressure drop? Okay. Yeah, here you can see next problem. An oil of viscosity 10 poise. So again, poise. So even I think at this moment, even the SI unit of viscosity is given, Newton second per meter square. You please once again convert that into poise also, so that you can remember all the problems in poise only. Okay. So oil of viscosity 10 poise is given, SI units divided by 10, or from SI units if you want to convert it into poise. for our what you can see reference. While what I'll do, I'll multiply with this 10, 1 into 10 Newton second per meter square, that is 1 poise. Okay. So that oil is flowing between two parallel plates which are fixed each other, which are kept at a distance of 50 mm apart. So please be careful. This 50 mm apart where the fixed plates are kept, it is again a vertical height. So vertical height between two plates, like you can remember like fixed plates, one is the floor, one is the roof. Okay, in a given room, if the flow of air is taking place, roof and floor, the distance between the roof and floor is 50 mm. So here width is still not given. We'll see. Find the rate of flow of oil between the plates. See here, rate of flow or discharge of oil between the plates if the drop of pressure in the length of 1.2 meter. So here clearly they have given length. Length of the flow is 1.2 meters. Between that, the pressure drop is already given in the problem. So pressure drop is P1 minus P2 or dou P. Dou P is for this length 0.3 Newton per centimeter cube. So this we have to convert in SI units. So it should be Newton per centimeter square actually. Then you can convert this into Newton per meter square. That will be pressure drop. Next point is the width of the plates is 200 mm. Now all of you focus on the dimensions of the channel. Height between these two plates is 50 meters apart. Sorry, 50 mm apart. So height is 50 mm. Width of the plates or width between these channel, you can imagine a channel, floor and top roof is of the metal plates, fixed metal plates parallel each other. That distance is 50 mm apart, and horizontal distance width between these flow channel is how much? 200 mm. One more dimension is given, the length of the flow. So length of the flow is mentioned in the problem. Yes.
So it should be a centimeter square, right? Pressure difference.
It should be centimeter square. It should not be centimeter cube. Here it is a mistake. So please note down this value, pressure drop 0.3 Newton per centimeter square. Then we can convert that into Newton per meter square. Okay. And length is also mentioned in this problem, 1.2 meters length of the flow. So using this, what we have to find out? What they're asking, find the rate of flow. So either you find out mass flow rate or the discharge. Okay, so that flow rate we are going to find out using these all details. Now directly recall the mass flow rate to find out what we know, that Q equal to velocity into area. All of you know this equation, velocity into area. Now go back to velocity. Now average velocity to find out for these type of channels where the plates are fixed and in between the oil is flowing, then recall this U bar. So U bar equation from the derivation we can recall, or you can recall this pressure difference formula itself, because we know the pressure difference and average velocity relation, that is P1 minus P2 equal to 12 mu into U bar into L divided by T square. T is the height between two plates. That is how much? That is 50 mm apart. That is T. L is given here 1.2 meters. Mu, U bar we need to find out. Mu is given. Viscosity is given 1 Newton second per meter square. It is mentioned in poise earlier. We converted it. Then P1 minus P2 is also mentioned in the problem. That is 0.3 Newton per centimeter square. So convert that into Newton per meter square. So here in this line also, it should be P1 minus P2 equal to 0.3 Newton per centimeter square. If you multiply this Newton per centimeter square with this 10 raised to 4, then it will be Newton per meter square. Okay. So now using this relation, one can find out average velocity, or else recall this equation, U bar. Whether you can use this equation or not, you can check. U bar you can find out as minus is just a direction. Magnitude, if you see, it is 1 by 12 mu. So mu is given in the problem. Dou p by dou x. So here what you can do, P1 minus P2 value you can substitute. What is P1 minus P2? P1 minus P2 is 0.3 into 10 raised to 4. So that you can substitute in this formula, dp. Dx is the length, 1.2 meters is also given. T is the height. T is the height. What is the height given? Height given is 50 mm. So all the values are known to us. So either you can go by this formula, that is U bar equal to 1 by 12 mu dou p by dou x into t square. That will also give us the average velocity, or else in this P1 minus P2 formula, we know P1 minus P2, we know T also, we also know this mu, this L. So as we know all the values, only left thing is U bar. So this also you can find out by this relation. So that is coming around, just a minute. Yes, here. In this, it is coming around U bar as 0.52 meter per second, the average velocity of the flow. Also check by this formula, we'll see. This U bar formula directly. U bar equal to 1 by 12 mu dou p by dou x into t square. This also you can check. Both should become same actually. Because if you see the both relations are also same. P1 minus P2 equal to, see here, dp equal to, if you write, it will be 12 mu into U bar into L. L is dx. See here, 12 mu into dx is L into U bar. Whatever the written here in the numerator is same as here. Divided by t square. So this t square will be divided. Both equations are same. And also the average velocity, whatever you find out from these two equations, is also should be 0.52 meter per second. Okay. So next is once you find out this velocity, area we can find out by using this width and height, 200 mm by 50 mm. So once you take this in meters, 0.52 meters, not 52, it is 50. See in the problem they have made some mistakes, printing mistakes are there. Please be careful. Sorry, average velocity is 0.52 meter per second is correct. Area is 0.20 meters into 0.05 meters. Okay. So once you multiply this meter into meter per second, it will be meter cube per second. So meter cube per second means it is a discharge value. So mass flow rate or the discharge value is meter cube per second. The value is 0.0052 meter cube per second. So either you can keep in meter cube per second. If you want to convert this in liter per second, Actually, liter per second answer is not required for us. Our answer required is in SI unit, that is meter cube per second. So you can keep this answer in 0.0052 meter cube per second. Okay. Is this understood to everyone? Compared to earlier problem, this problem is simpler because length is given, width is given, height is also given. And even P1 minus P2 pressure drop is also given. Shall I take the last problem? Okay, answer is 0.5208. Okay. Just a minute. 0052. Okay, next class we'll continue with the last problem and compressible flow. Pushpa, can you tell me what is this unit or which value you have found out 0.5208?
Average velocity. By
Liter per
other
second.
components.
Okay, yes. 0.5208 is average velocity formula, no?
Yes, sir.
Okay, thank you. So see here, all of you. Pushpa has got 0.5208 as the average velocity from the average velocity formula. I think you have used this formula, correct? Magnitude.
Yes,
So
sir.
this is the value. Or if you go by this formula, U bar is around. Also, I think it will come same. That will be also 0.5208 only, I think, correct?
Yes, sir.
Okay. So thank you very much. So today we'll stop the class at this point. Next class we'll take one more problem to just recall the concepts what we have learned in the today's class, and we'll take the last chapter, that is compressible flow, from next Monday. Okay.